Welcome back to The Explainer. Today, we're getting into one of the most exciting developments in AI architecture right now. If you've been following the space, you already know Retrieval-Augmented Generation, or RAG, is an absolute game changer. But today, we're skipping the high-level theory. We're going under the hood to look at a blueprint for building a real-world RAG system from the ground up, using the exact concepts engineers are working with right now. Okay, let's dive right into this. What makes a RAG system actually work reliably, efficiently, and accurately when you deploy it out there in the wild? It's one thing to know the theory, the idea of giving an AI a search engine so it can look up facts before it speaks, but building it, that requires treating this like a high-performance engine. We've got to understand the parts, the fuel, and the precise control dials that make the whole shebang run.
Act 1. Choosing the engine. Selecting your RAG LLM.
So the absolute first critical step in your pipeline is picking the right foundational model. Because, trust me, not all engines are created equal for this specific job. When engineers choose an LLM for RAG, they evaluate a few core attributes. Infrastructure compatibility and licensing terms, those just tell you if you can legally and technically run the thing. Inference speed tells you if it's fast enough for your users. But look at that very first point, reading comprehension ability. In a normal, everyday setup, you want an AI that just knows a lot of trivia. But in a RAG system, reading comprehension is absolutely crucial. It dictates how effectively the model processes the context you retrieve for it to generate an accurate answer. It doesn't need to have memorized the entire internet. It just needs to be an unbelievably good reader of the specific documents you hand it.
So the crucial point here is a massive real-world trade-off. Context window size is vital, right? A longer context window means your RAG system can feed way more relevant data chunks to the model. But you can't just pump infinite data in there. You have to balance that massive context size against hard limits, specifically cost and latency. A bigger context window means more computation, which literally means it costs more money and takes way longer to get an answer.
Act 2. The fuel. Standard versus RAG prompts.
And this brilliantly illustrates how we actually power that engine we just picked. How we prompt a RAG engine is fundamentally different from a standard LLM. Think about a standard, non-RAG setup. You give the model a user query, maybe some optional instructions, and it generates a response based entirely on the knowledge it gained during its initial training. It's relying entirely on its internal memory. But contrast that with a RAG prompt. You have the user query, the instructions, and the explicitly provided relevant context. Here, the LLM generates a response solely based on that context fuel. It's a massive paradigm shift. You're strictly instructing the model to bypass its own internal and potentially hallucinated memory and build its answer using only the exact facts you just handed it.
Act 3. The control room. Tuning the hyperparameters.
All right, we have the engine and we have the fuel. Now we're stepping boldly into the control room to turn some highly specific technical dials. Tuning a RAG pipeline means tweaking variables to get the output just right, which we basically divide into retrieval and generation phases. Let's kick off a rapid-fire sequence of the retrieval dials, starting with chunk size. Before you can retrieve text, you gotta chop your documents up into searchable pieces. Chunk size dictates the exact amount of text put into a segment before it gets embedded. This single dial influences the foundational context granularity of everything you do. If your chunk is too big, the specific answer gets completely lost in a sea of irrelevant words, but if it's too small, the model might not have enough surrounding context to even understand the sentence.
Moving seamlessly from that, we have chunk overlap. Imagine cutting a book up into paragraphs. What happens if a totally crucial thought starts at the very end of paragraph 1 and finishes in paragraph 2? You'd lose it, right? Chunk overlap fixes this by literally repeating a set of tokens at the chunk boundaries. It acts as the connective tissue that stops crucial information from falling through the cracks between segments, preserving the important context across your database.
Next up is embedding dimensionality. Here's where text essentially becomes math. When we store these chunks, we represent them as vectors, basically just lists of numbers. Embedding dimensionality is the specific vector size used to represent that text. And turning this dial has a massive impact. It directly affects your retrieval precision, how accurately the system finds the right math equation for your text, and your database efficiency. Higher dimensions might capture a lot more subtle nuance, but man, they eat up way more space and compute power.
Let's move to Top-K and see how this builds on our previous metrics. When a user asks a question, your database finds matching chunks. Top-K sets the exact number of most similar chunks returned by the system to feed into the prompt. If your Top-K is 5, it returns the 5 best matches. It's pretty straightforward, but this dial directly impacts the recall and the context diversity in your final response.
But wait,
You can't just let any chunk in just because it made the top 5, right? That is exactly where the retrieval threshold comes in. Think of this as the strict bouncer at the door of your LLM. It's a hard similarity cutoff that filters retrieved results. Even if a chunk is sitting there in the top K, if it doesn't meet this minimum similarity score, it gets rejected. This makes absolutely sure that only truly relevant stuff makes it into the LLM's view, keeping your context window pure and focused.
Okay, let's pivot from the retrieval dials over to the generation dials. We are shifting our focus from how the system finds the right data to controlling how the final answer is actually written out by the engine. This whole phase is an exercise in balancing creativity versus determinism.
The absolute rock star of these generation dials is temperature. Temperature controls the randomness of the generated text. It is the precise dial you turn to find the perfect balance. If you dial the temperature way down, the model becomes highly deterministic, factual, and strictly adheres to the data, which honestly is usually exactly what you want in a business RAG system. But if you turn it up, it introduces randomness, allowing for more creative, varied, but potentially much less predictable outputs. And finally, we have the max output length. This does exactly what it sounds like. It limits the number of tokens the model is allowed to generate in its response. You can think of this as the final safety brake on your engine. By capping the output, you stop the engine from rambling on endlessly. And crucially, you manage the computational bill you have to pay. Every single token generated costs money and time, so putting a ceiling on it protects your resources.
So there you have it. We've walked through the blueprint. You know how to pick the engine based on reading comprehension. You've seen how the RAG prompt changes the fuel by relying solely on explicitly provided context, and you've stepped into the control room to see the actual hyperparameters, from chunking down to temperature, that dictate success. You literally have the dials in your hands now. The real-world engineering challenge is up to you. How are you going to balance creativity, cost, and precision to build the perfect RAG pipeline for your own specific needs? Thank you for exploring this with me today on The Explainer. I really hope this structured look empowers you to build smarter, faster AI systems. Keep learning, keep tuning, and I'll catch you on the next Explainer.